All right, screencast on the position versus time and velocity versus time worksheet. Two things you need to try and think about when you do this worksheet. One is the graphing your motion lab that we did where you walked in front of the motion detectors. Think about what happened when you did those things and try to relate that to these questions. And secondly, we will have done a demo where you guys get in front and try to match graphs as a class. So think of those two things as you try to answer these questions. Now, some I'm going to help you with, others are all on your own. But if you look at this first graph, position versus time. So this is a position versus time graph. Now, remember, we've talked about this. When the line is a straight line in a position versus time graph, that means that that would be a constant velocity. That would mean that this biker here is traveling at the same speed the entire time. If, let's say, he was traveling really fast at the beginning, it would be a steep slope. Then as he slows down, the slope is going to curve. And as he comes to a stop, the line would then go horizontal, right? So keep those things in mind when we're doing these problems. And remember that the greater the slope, the faster the person is going, because they're covering more distance. If you look here at this point, at point A, in the same amount of time, all right, they are covering a longer distance than B, who would only be covering this amount of distance in a period of time. All right. All right. That should be pretty straightforward there. So do the cyclists start at the same point? If not, which one starts ahead? So remember, this is a position and this is time 0. So look and see, are they starting at the same position when the race begins or the journey begins? And once again, when we do these things, always read. This has 3 different questions it's asking you. Do the cyclists start at the same point? So that's yes or no. If not, which one starts ahead? So you'll need to explain that one. And then how do you know that? That's the most important part here. So make sure you do not forget to put in the how you know, all right, in your answer. At t equals 7 seconds, which cyclist is ahead? So on the time portion of this graph, here we have 5 seconds. If you go halfway between 0 and 5, you're going to know that that's going to be 2.5 seconds. So if we go out that same distance here to right here, we'll know that that is approximately 7.5 seconds. So at the 7-second mark, it's going to be a little short of here. You're going to then go up and look and see which bicyclist is ahead at that time. And then once again, once you've put down that answer, write down how you know that. Which cyclist is faster at t equals 3 seconds? And how do you know? Well, coming back up here, remember this is 5 seconds, and then halfway is 2.5 seconds. So you can figure that one out. Are their velocities equal at any time? And how do you know that? So remember, velocity is distance, or in this case, displacement divided by time. And think about what I said at the beginning of this video when we talk about what the slope of the line means. What is happening at the intersection of lines A and B? So intersection, right, is where they come together, like an intersection on a road. And so they're talking about this point right here. What is happening at that point? On to the second page. Determine the average velocity of the objects in the following position versus time graphs. So what is the velocity of the object? Include a direction. So how are we going to figure that out? Well, to do velocity, we have to know the equation. All right, and velocity equals displacement divided by time. Or in this case, time. And so when you look at the displacement, how far did they travel? Well, what we're going to do is we're going to start here, and they are at 5 kilometers. At the end of the period of time, all right, they are here, which means that they have gone to the 2 kilometer mark. So now if you look at the distance between these two, 1, 2, 3. So if you took 5 minus 2, you would end up with 3 kilometers, or counting up 1, 2, 3. So the displacement was 3 kilometers. So that's going to be 3 km. And then you're going to divide that by the time it took. Well, they started here at 0 and they ended here at 6. So it was 6 seconds. So we do our math, and notice that when you write your answer, I want both the number that you're going to get and the unit. And this is a velocity, so it's going to make sense that it's in kilometers. I'm really having a tough time with that, isn't it? It's going to be in kilometers per second. Funny. It's just, sometimes it works great, sometimes it doesn't. All right. And don't forget your number here. Now, this one you're going to do the same way. All right. So you have this one above to look at to help you. Then on number 8, it says draw the velocity versus time graph for an object whose motion is shown in the position versus time graphs shown below. So this is a good one, because when we first did our Graphing Your Motion lab, we were dealing with position versus time graphs. However, this is a velocity versus time graph, right? And it's always good to think of velocity in terms of speed in a given direction. So if you just think of it as speed, then you should be okay. So if we look here at this graph, it's telling us that if we wanted to figure out the speed, that would be distance divided by time. Well, look here. The distance traveled here is 1 meter. How long did it take to go 1 meter? It took 1 second. All right. It took 2 meters. We traveled 2 seconds. 3 meters, 3 seconds. So when you take 1 divided by 1, or 2 divided by 2, or 3 divided by 3, every single time you're going to get the same answer, which is it's a velocity of 1 meter per second. I think I'm going to give up on the units there. 1 meter per second, which you'd see over here. Now, we talked about this earlier. A straight line in a position versus time graph means a constant velocity, and we just proved that, didn't we? Every single time the rise and the run are the same. Up 1 over 1, up 1 over 1, up 1 over 1. And the entire time, no matter what 2 points you pick, 6 meters divided by 6 seconds is going to give you 1 meter per second. So when we graph that over here, we need it to stay at a constant speed of 1 meter per second. So we're going to start here, and we're going to follow this line across for 6 seconds, because it travels at 1 meter per second for 6 seconds. So the same information on 2 different graphs, and it looks different. This one right here, challenge problem. This is kind of a hard one. I'll put a star by it because we're going to call that a challenge problem. And see if you can figure out the velocity. Now, I'll give you a hint. Figure out the rise over the run for the velocity here. And then notice now you're heading towards the detector, because the distance is decreasing. And when you are heading towards the detector, you're going to have a negative velocity, meaning that you're going to be running down into this negative value because it has that line there. All right. The rest of them, I think, are pretty straightforward. I'm running out of time on the cast, so hopefully that helps.